Hello, my name is Giacomo De Rossi and I'm here to present you a multimodal learning system for action segmentation to control assistant surgeon robots. I will start by presenting the SARAS project. SARAS stands for Smart Autonomous Robotic Assistant Surgeon, and it intends to emulate the actions performed by the assistant surgeon during robotic minimally invasive surgery. In this type of operations, a surgeon usually teleoperates a Da Vinci surgical system, sitting away from the patient, whereas the assistant surgeon operates standard laparoscopy tools standing next to the patient. The aim of the project is to provide a solo surgery system to allow for only the main surgeon to single-handedly complete the required surgical task, thus freeing the assistant surgeon to attend other patients. This will have the clear benefit of reducing the required personnel for robotic minimally invasive surgery, and also for standard laparoscopy operations if needed, with the benefit of improving patient care and cutting costs. One key element of the overall SARAS strategy is to achieve the solo surgery architecture, which requires the system to automatically segment the sequence of actions being performed to drive a pair of custom-made robots, which hold the standard laparoscopy tools. The picture shows a mock setup involving the Da Vinci teleoperated tools, letter A, the Da Vinci stereoscopic endoscope, letter C, and the SARAS manipulators, letter B, which are positioned over a phantom for prostatectomy operations. Given the underlying variety and complexity of the data, the solution verted on a neural network. The final architecture, called Encoder-Decoder Spatial Kinematic ResNet, represents a multimodal action segmentation solution that operates in both the spatial and temporal domains. For the spatial domain, the network employs a ResNet structure to generate features from RGB images augmented with a motion history image channel, with the latter being used to maintain a trace of the motion through the scene of all moving agents. In addition, the information from the kinematics of the robots is concatenated to the ResNet features to create a multimodal architecture that harvests all possible information available. The spatial kinematic network produces one-shot evaluations for each time step of the operation that are inserted into a circular input buffer for the subsequent temporal analysis. The latter adopts a temporal convolution network structure that filters in the temporal domain all the noise present among the spatial data to generate a cleaner segmentation of the different actions being performed. The structure guarantees causality and real-time data processing. The comparison with the state-of-the-art for the median user of the JIGSAWS dataset indicates that the network outperforms the methods currently available while maintaining the causality constraint. This is especially true in the confrontation with other neural network structures reported in the bottom half of the table that tend to produce higher results when compared with statistical analysis tools presented in the top of half. The only score that suffers in the comparison, the F1 score, is a consequence of the missing future data in the evaluation of each data point. Here we can see a custom results on the SARAS dataset, with the actions being performed by the main surgeon and the assistant surgeon, 8 actions in total, and the robots tasked with picking up a token from the scene. Now the surgeon is actually picking up the token, and the SARAS starts the operation of capturing the token taken from the surgeon and place it to the target corresponding with the color. On the top, we can see the sequence of actions being performed and segmented in real time. Thank you for your attention, and please follow us on SARAS H2020.